This is my lab report for Lab 4, Oscillations. The purpose of this lab is to model the energy principle through experimental oscillation. Then, using that data, creating a computational model using net forces and the energy principle to model the oscillation. The fundamental principles of physics in this lab are the energy principle, net forces, and periods of oscillation. In this experiment, I will track the position of an oscillating mass suspended from a spring in 2D, then create a computational model that mimics the experimental data. Then I will use the energy principle to calculate and graph different potential energies that should sum to 0 joules of total energy. The system is the mass, the spring, and the earth, while there is nothing in the surroundings. This is the video that will be used to track the oscillation. As shown in this clip, the mass is released from rest and allowed to oscillate freely. This is the tracker data generated from the previous video. As can be seen, the mass oscillates in both the x and y directions, creating a two-dimensional oscillation. And this is the computational model generated from the tracker data. This also includes comparisons to the real data, as that data was imported into the model via a CSV file. The blue ball and path represents the computational model, while the red ball moves based on the real position data from the CSV file. The graph in the top right represents the changes in kinetic energy and spring and gravitational potential energies as the ball moves, with the total energy always equaling 0 joules. Lastly, the bottom two graphs compare the x and y positions of the model and experimental data. This is the code used to generate the computational model. To begin, the mass of the object was 0.402 kilograms, while the initial position was the one recorded in the tracker data. The ball starts at rest. Next, the constants were defined, including gravity, the spring constant of the spring in experiment, and the relaxed length of the spring. Also, the spring stretch was calculated to be used in the spring force equation. Next, the total energy of the system at the start was calculated, including the kinetic energy and the gravitational and spring potential energies, which all sum to the total energy. Next, the net force was calculated using the force of gravity and the spring force, and the second law was applied to the model. Also, the spring was updated in each iteration. Lastly, the energies were updated in each iteration, and the changes in energy were calculated between each iteration. As is the case in any experiment, there were sources of error and subsequent assumptions made in the model of the experiment. To begin, in the experiment, drag might have affected the position of the mass without being accounted for. Also, the tracking might have been imperfect due to the frame rate of the video or human error. Some assumptions made in the computational model include not considering the effect of drag on the mass and much smaller time steps, which might cause variations between the experimental and computational data. Does the computational model satisfy the energy principle? To begin, it is important to reiterate that the system contains the mass, the spring, and the earth, while there is nothing in the surroundings. As a result, the surroundings do no work, and since the total energy of the system is conserved, according to the energy principle, the total energy should always be equal to 0 joules at any point in the model, as shown in the graph by the orange line. Therefore, the model satisfies the energy principle. How do the periods of oscillation in the x direction differ from those of the y direction? The average period of oscillation in the x direction is 1.638 seconds, which is slightly higher than the 1.524 seconds in the y direction. This means that the mass takes longer to return to its original x position than its original y position, so it is slightly more displaced in the x direction, creating an elliptical oscillation. In sum, this experiment achieved many goals, including understanding the energy principle through 2D oscillation and modeling and comparing the oscillation in a computational model using net forces and the energy principle. In this experiment, it was found that the energy principle is always followed by both experimental and computational data. And this is proven by the fact that the total energy of the system is constant throughout the experiment and model. Thank you for watching this lab report.